A quick explanation of paint fence, leak code problem 276. So you're painting a fence of n posts with k different colors. You must paint the posts following these rules. Every post must be painted exactly one color, and there cannot be 3 or more consecutive posts with the same color. Given two integers n and k, return the number of ways you can paint the fence. So first off, sort of looking at this problem, we can sort of see it's like a combinatorics problem, especially with this first point. Every post must be painted exactly, or you're painting a fence. You have k different colors to choose from for each n posts. If we were just working off of the sort of first point, which is kind of like an obvious point, right? It'd just be n to the k, k to the n would be the number of different combinations we have. But this second point, there cannot be 3 or more consecutive posts, kind of messes with that answer. We cannot have, for example, 3 reds in a row or 3 blues in a row. So sort of looking at how we might go about solving it with this condition in place. So first looking at like a very basic example, n equals 3, k equals 2, first understanding the problem. So there are two, so normally the number of combinations there are is just 2 to the 3 equals 8. However, this condition right here, there cannot be 3 or more consecutive. 0, 0, 0 doesn't work, and 1, 1, 1 does not work. So a minus 2, the answer should be equal to 6. Yeah, pretty straightforward stuff with that first case. And then let's look at some bigger numbers and how might we handle them, especially from the computer's perspective. So in this case, each grid sort of represents a post. Probably should have explained that earlier. But so here it's 4 posts and 4 different colors. So in this case, if we represent each color as 0, 1, 2, or 3, just for the sake of clarity or ease of writing. Right off the bat, we can sort of see the answer is not so clear anymore, right? Because there are a bunch of different random combinations in here that could be like 0, 0, 0, 1, or maybe it's 2, 2, 2, 1, or maybe it's 1, 2, 2, 2. We don't really know. What we can sort of go about doing is first start decomposing our problem. As we can see, this array is of length 4, so we can mark these 0, 1, 2, 3 indices. We're going to get rid of those color representations for now. So these are just our indices. And if we were to sort of break our problem into sub-problems following a sort of dynamic programming approach, let's say we can start with observing that, okay, if we just had our first grid, there are k different colors to choose from, right? So it could be 0, 1, 2, or 3, where 0 to 3 represents a different color. So the answer in this box for just this segment right here, just this segment is 4, right? And then same thing for the next one, 16, right? Building off of our previous one, we know there are 4, so now we add 4 more colors. Now it can be 0, 0, or 0, 1, 0, 2, 0, 3, or 1, 0, 1, 1. So it builds up to 16. 4 times 4 is 16, right? But here is where things start to get slightly trickier, right? So obviously we cannot just multiply by 4 because there will be duplicates. Precisely, there will be 4 duplicates in this case because there are 4 colors, right? If normally there would be, because up to this point we have 3 posts, right? So if we have 3 posts, it would just be 4 to the 3 equals 64. But 4 of these 64 are all the same color. same color. So 4 of these 64 are invalid based on this secondary condition. Invalid, right? So we would actually only have 60 here because we lose the 0, 0, 0, we lose the 1, 1, 1, and we lose 2, 2, 2, and we lose 3, 3, 3. And sort of carrying over to our last grid, how might we be able to bring this second grid's information, once again following a dynamic programming approach, using this information up here and transferring it to help us solve for that final grid, which will just be our final answer. Well, first of all, we can note, okay, we see that for the second index, for three items of, or three posts of 4 colors, answer is equal to 60, right? There are 60, importantly, 60 valid combinations, not just 60 combinations, 60 valid combinations, right? And based off of that, once again, we can't just multiply by 4, right? Because of these 60 valid combinations, if we sort of map this down here into these 3, there will be a certain amount of 2 length. There will be a certain amount of subset of these 60 where the last 2 are the same color. So for example, of these 60 valid, let's say there will be this 0, 0 at the end, starting with a 1, is a valid combination within the 60, right? Because there is no 3 length that is all the same color, right? Obviously, if this was 0, 0, it wouldn't even be valid, and it wouldn't be within that 60 subset. So it's a 1, 0, 0. So that's a valid, but in this case, if we add another 0 here, it would be invalid. So we can't just multiply by 4, same as before. So, and obviously 2, same thing. It also is valid within the previous one, within this previous 3 post combination, but it is not valid if we add a 0 here. But it is valid, however, note, if we do 1, 2, or 3. So we could say whatever these are, it doesn't really matter, 1, 1. As long as these last 2 are the same within these 60 valid, then we know that some of these combinations, this next color combinations will not work. So we can sort of our first approach would be to sort of try to figure out how many of these 60 valid have these length 2 sequences, right? Length 2, 2 items, 2 posts, same color. How many of these 60 have these, right? So here, there are 60 before, and to figure out how many there are that are length 2, we would have to take the number of combinations in this subset and multiply it with these combinations as well. And it may be a pretty skewed number. And the computation actually becomes quite complicated after you begin to have longer arrays. Because what you end up having to do is for every combination of 2, you have to look at this previous number. Because for every, so like let's say these, because right now what's happening, right, is these 2 1s are valid within this set of 3, but once we add another number, it might not be valid anymore. And the same thing might happen over here where we try to figure out the number of combinations over here, in this case, it's just k, but let's say it was a much longer array. It might be many more combinations. We would have to scale all the way back to the beginning, iterating, decrementing by 2 every time to look, okay, how many are over here? How many are over here? And you'll see that pattern sort of arise if you try it out for yourself. And you sort of come to the realization that that sort of approach is pretty complicated and doesn't work very well. So like that sort of approach is where we try to find, okay, how many length 2 posts are the same color? We subtract that, and then we multiply by k. In this case, we multiply by 4 at the end to find the number of combinations at this index y, at this spot. But it doesn't work too well because it's computation heavy. And if we could just figure out what is x instantly, then this problem becomes much more simpler. So one way we can sort of go about that is using 2 arrays. So instead of this approach where we just store the answer in one array, so this is a DP approach, right? We're using our previous answer to build our next answer. So it's like it's sub problem. It's caching the old computations and using them again. We're going to do that again, but this time we're just going to store a bit more information. So we're going to store the length 2 posts at each stage. That way we don't have to go back and compute every single time. And so how might we go about doing that? So first array is going to be number of valid combinations. So we're going to use that n equals 4, k equals 4 example again. Number of valid combinations with length 2 repetition at the end. So with, right? And the second array is going to be number of valid comb without length 2 reps. This is kind of there's quite a bit of intuition for why we would sort of set up 2 arrays like this now, right? Because at every stage, we want to know this value. This value is, what's going on here? This value is very important to us for computing each value. So how would this problem be approached now? And of course, it's key to note that if we sum the value, all of, like, for example, x, if we sum up x0 and y0, that just gives us the total number of valid combinations, right? If we just sum them up, because that would give us number of valid repetitions with and number of valid combinations without, right? So together, it would be with and without, and it would just give us all of the valid combinations. So we're getting this out of the way. So let's first build the first few elements of our DP array. So this is still a DP approach, but we're just storing slightly more information in a more useful manner. Because from our previous DP, we saw that we had to go back and retrieve this length 2 posts, that same color from before. So because we saw this, we built 2 arrays. So sort of this top array is the key thing we want to be adding here. And if we sort of build out the answer for n equals 4 and k equals 4 once again, so what is the number of valid combinations with length 2 repetition at the end? So obviously it's 0 in the beginning, right? There is no way you can have a length 2 repetition at the end with a length 1 sequence. That just doesn't make sense. So here it would be k, right? K different colors, 4 different colors. Number of valid combinations with length 2 repetition at the end for this second index. This time, the value is going to just be k, right? And at the one index over here, it would just be 16 minus k, right? Because you have 16 items, 16 possible or 4 from before, and then you multiply it by 4, but then there are 4 that repeat, right? So like 0, 0 repeats, 1, 1 repeats. Basically, we're putting 0, 0, 1, 1, 2, 2, and 3, 3 over here, and we're putting the rest over here, the different ones. So now is the cool part. We can see that at each stage, we can use just the information from the previous stage to build this the answer to the next subproblem in O of 1 time. And the key here is to always only build valid combinations. So let's take a look at what our problem is asking us to do. So at the second index, we're now wondering, okay, how many valid combinations are there with length 2 right here? How many valid combinations are there with length 2 repetition at the end? If our previous sequence already has length 2 repetition at the end, then no matter what we put at the end, it is impossible to create a valid combination with length 2 repetition at the end, right? For example, if I put 0, this is not valid anymore because this is already a sequence of 2. We put one more, it'll be a sequence of 3. If we put a different number from what this previous number is, it doesn't have a repetition of 2 anymore either. So no matter what k is, it could be 1, it could be 0 all the way up to k. It doesn't matter what it is. There will never be a length 2 repetition sequence. In other words, this k right here, I'm going to sort of mark it in green. This k does not contribute to any of these next values. None of these k will go into building this value right here. However, we will note that these values down here will, however, build into this spot. So how will it build? Because we know these numbers, the last two, the ending two numbers are different. For example, they might be 0, 1. We know they are different. That's what it means for it to be in this array. We know that the number of if we add another number, the number of valid combinations with length 2 repetition at the end is equal to the number of numbers in this sequence. So in this case, because it's 16 minus k, in the next iteration, this value would also just be 16 minus k. Because we're looking at number of valid combinations with length 2 repetition at the end. The only way to achieve length 2 repetition at the end is for this x value, this next color, to match this color. So it does not provide any new combinations. For example, if we had 4 combinations, well, like hypothetically, let's just say all of a sudden we have 4 combinations here. We have 4 combinations and they are 0, 1. And these are all combinations that don't have repeating ending numbers. So it might be 2, 1, 1, 2, and 0, 2. This next number has to be 1 for it to be fit into this condition of length 2 repetition at the end. And this has to be 1. This has to be 2. This has to be 2. So how many combinations does it end up with? It's just the same amount. So we could just take this number from the previous index and just migrate it over to there. And that's our new value for valid combination with length 2 repetition at the end. And now we want to take a look at what value can go into here, right? So let's do the same sort of analysis as what we just did earlier with the repeating ones. If we do the same sort of analysis, we end up seeing that if the previous two are repeating, the only way to achieve non-repeating is to just have a number that's different from this. So the number of possibilities that we have more of, so this number, if we had k different colors, k colors to choose from, the number of valid colors that can go into here is just k minus 1, right? The only number in this case that cannot be is 1. And it's the same thing for all of them. So we can just take, so there are k minus 1 multiplied by the number of combinations in this subsequence. That's the number of combinations there are from this top segment. So sort of taking a look at what that would sort of look like. If we use a slightly different color, we would take this k, we take k, we do k times k minus 1, but that's not the whole part of the equation, right? So we're going to put this y value over here, k times k minus 1, and then we still have to add the number of combinations from itself, right? Because there are 16 minus k combinations, right here, 16 minus k combinations that are different colors. And these can contribute to number of valid combinations without length 2 repetition at the end as well. So this can contribute as well in the same manner as the previous one. It can just be k minus 1 different colors over here. It just needs to be different from the previous number. So we just take this 16 minus k and we multiply it by k minus 1 as well. So ultimately y is equal to k times k minus 1 plus 16 minus k minus 1. All right? And then this is a pattern that goes on throughout the entire array. And by the time we reach the end, we just sum up the number of these top combinations, the number of valid combination with length 2, plus the number of valid combination without length 2, and that's just the total number of combinations. So we end up being able to solve this problem in O of n time, right, where n is the number of posts. So we just do one iteration on 2 arrays, storing these 2 values as our DP values, and we end up building our answer. And so more concretely, sort of defining, rather than using these random variables, sort of clearly defining what this algebraic expression looks like. If we were to say y1 is the top one, so we have y0 all the way up to yk, right? And then we have x0 all the way up to xn. So these are all values in top array. So these are the repetition ones. X has the double repetition, or the single repeat. So sort of defining a very algebraic, very formulaic method of solving this, and obviously very simple to implement in a computer program as well, is we can just say x, after we can set x0 and y0, sort of like the base cases of this problem, instantly, right? Instantly we know x0 is just 0 and y0 is just k. So after we get that out of the way, we can say from there on out, we have a very formulaic expression that we can use to build all the way up to xn and yn, and that is x at I is equal to y of 0, or sorry, y is equal to y of I minus 1, right? Remember, this is just saying, or yi at index I minus 1. This is just that transfer that we saw right here, where we move this 16 minus k, we took 16 minus k and put it right there, right? Because we know this, it will not build from itself, because a double, if we add another one, it cannot still be a double repetition, right? And then same thing for that bottom, yi, but this one's slightly different. We have to do xi minus 1 multiplied by k minus 1 plus x plus yi minus 1 times k minus 1. And of course, we have to put these in brackets to make sure our operations are in the right order. And with these two formulas, you iterate one at a time. You eventually get to the end. You get to x sub n, y sub n, and then the return answer, you just end up returning x of n plus x sub n plus y sub n.